Let us take an example and see how we can obtain an estimate for the derivative. Suppose say we are asked to find f dashed at 0.25 from the table of values which are given using divided difference formula. So, I have used the short notation dd, that is divided difference formula, and the table of values are given here corresponding to x0, x1, x2, x3. The function values are given. So, I form the divided difference table. So, compute the first order difference. We know the entry here is this minus this divided by x1 minus x0. Then the second entry is this minus this by x2 minus x0, and so on. So, we compute the first order divided difference. The second order divided difference will be this minus this divided by, it involves the points x2, x1, x0. So, by x2 minus x0, that will give you this difference, and so on. So, we form the divided difference table. So, we require f of x which is approximated by a polynomial p3 of x which is of degree at most 3 given information at 4 points. So, we know that p3 of x is given by 0.1761 plus this entry into x minus x0. The next term will be this entry into x minus x0, x minus x1, and the last term will be this into x minus x0, x minus x1, x minus x2. So, I compute f dashed of x. So, f dashed of x will be p3 dashed of x. So, we take the derivative on the right hand side. So, we have written down the expression for the derivative on the right hand side. Now, we require the derivative at some point f dashed at 0.25. So, that will be estimated by p3 dashed at 0.25. So, we observe that if we substitute x as 0.25 on the right hand side, we will get an estimate for f dashed of 0.25. And you know what are x0, x1, x2, they are given in the table. So, if you substitute, you end up with the value which turns out to be 1.7363. So, this point x is not any of these nodal points. F dashed at 0.25, 0.25 is somewhere here. So, you require the derivative of the function to be estimated at this point. So, you used the divided difference formula and obtained an estimate at any point x in the interval. The function derivative can be estimated, and the value is the value of the derivative at that point of the interpolating polynomial that interpolates the function. So, this illustrates the theorem that we had proved in the previous class. So, one can therefore use polynomial interpolation to derive numerical differentiation formulas by simply taking the derivative of the interpolating polynomial that reconstructs the function or approximates the function at a set of discrete points, and depending upon the order of the derivative for which you require an estimate, you can differentiate the interpolating polynomial and then evaluate this estimate at the required point in the interval. So, now we move over to another method of getting estimates. So, I introduce what is known as the differential operator. So, the differential operator, so let us denote it by D. This operator is such that D on f of x is nothing but d by dx of f. D square on f of x is d square f by dx square. So, the nth derivative on f will be the nth derivative of f with respect to x. We know that the shift operator E, when it operates on f, gives you the value at the next point. So, we consider these details for equally spaced points. So, let the information be given. So, E when operates on f of x is f of x plus h, which by Taylor theorem is f of x plus h f dashed of x plus h square by factorial 2 f double dashed of x, f triple dashed of x, and so on. F of x plus h into f dashed is d on f of x plus h square by factorial 2 d square on f of x plus h cubed by factorial 3 into d cubed on f of x plus etc. So, we have E on f of x to be equal to 1 plus h d plus h square by factorial 2 d square plus h cubed by factorial 3 d cubed plus etc. This operator operating on f of x. But we see that it is of the form 1 plus hd the whole square by factorial 2 plus hd the whole cube by factorial 3 and so on operating on f of x. So, it is e to the power of hd on f of x. So, E when it operates on f of x plays the same role as the operator e power hd when it operates on f of x. So, E is e to the power of hd. So, e to the power of hd, what is E? We have already shown in terms of the forward difference operator delta, as E is 1 plus delta. So, we have hd to be equal to log 1 plus delta. So, d is 1 by h log 1 plus delta. So, it is 1 by h into delta minus del square by factor by 2 plus del cube by 3 and so on. So, that is the derivative operator in terms of the forward difference operator. We also have obtained the relationship that connects delta with E, that is, it is E minus 1 by E, or I can give E in terms of the backward difference operator as 1 minus delta power minus 1. So, if I substitute that, e power hd is 1 minus delta power minus 1. So, hd will be log 1 minus delta power minus 1. So, minus log 1 minus delta. So, d is also minus 1 by h into log 1 minus delta is delta plus del square by 2 plus del cube by 3 and so on. So, the operator d can also be given in terms of the backward interpolation operator. So, these relations can be used to obtain derivative of a function. So, here we have obtained the expression for the first derivative, namely d. What will be d square if I want the second derivative? It is d on d. So, this operating on itself. So, I can write down it is 1 by h square into delta minus del square by 2 plus del cube by 3 etc. operating on delta minus del square by 2 plus del cube by 3 etc. So, I can compute the result and write down d square in terms of the forward difference operator, and higher order derivatives can be successively obtained in terms of the forward difference operator. The same thing can be done in respect of the backward difference operator, and higher order derivatives can be obtained if we know information about the backward difference operators of different orders. So, 1 by h square into del square minus del cubed plus 11 by 12 del power 4 minus 5 by 6 del power 5 plus etc. And similarly, in terms of the backward difference operator, it is 1 by h square into del square plus del cubed plus 11 by 12 del power 4 plus 5 by 6 into del to the power of 5 plus etc. Again, note that use these expressions for the first order derivative, second order derivative, which is given in terms of the forward difference operator. If you require an estimate of the derivative of a function very close to the beginning of the table of values, and similarly use the information here for computing the derivatives of a function whose values are prescribed near the end of the table. Then you will be able to get estimates which make use of the information in the beginning of the table as well as the information at the end of the table, according as you use the forward difference table or a backward difference table. So, let us now take an example and compute an estimate for certain derivatives. So, suppose say you are asked to compute f double dashed at 0, and the table of values are given at 0, 0.2, 0.4, 0.6, 0.8 and 1, and the function values are 1, 1.16, 3.56, 13.96, 41.96, 101.00. So, f double dashed at 0 is asked, it is in the beginning of the table. So, I shall form the forward difference table and use that information. So, the first order forward difference will give me 0.16, 2.4, 10.4, 28, 59.04. Then the second order differences will be 2.24, 8, 17.6 and 31.04, and the third order differences are 5.76, 9.6, 13.44. The fourth order differences will be 3.84, 3.84 and the fifth order differences will be 0. So, I require now f double dashed at 0. So, it is d square f evaluated at 0. An estimate can be got using the forward difference operator, which is 1 by h square into del square minus del cubed plus 11 by 12 del power 4 minus 5 by 6 del power 5, right, plus etc. The higher order differences will all be 0. So, I can close this. So, where this on where I require the second derivative of f at 0. So, this on f of x naught. So, that will be 1 by h square. What is h? The difference between any two successive nodes, namely 0.2. So, 1 by 0.2 the whole square into del square f of x naught. So, it starts with del square f of x naught, which is 2.24 minus del cubed f of x naught. So, 5.76 plus 11 by 12 del power 4 f of x naught into 3.84. then minus 5 by 6 into del power 5 f of x naught, which is 0. So, this is what I need to evaluate, and if you compute this, the result turns out to be say 0. So, the second derivative evaluated at 0 is an estimate which is obtained from this table of values. In addition, if you are asked to say compute f dashed at point 2, suppose say you are asked to get f dashed at point 2. So, you can still make use of this forward difference table, where you can forget about the information that is given to you along this leading diagonal. Say, think that you are given the table of values starting from point 2. So, f dashed at point 2 will be approximated or is equal to df at 0, and it is approximated by 1 by h into delta minus del square by 2 plus del cube by 3 minus del power 4 by 4 and so on f at 0. So, this will be your x naught now, and so this is f naught. So, this is the first order difference, the second order difference, the third order difference, and this will be the fourth order difference. So, the information is available at all these points, and so substituting this, you will get, this will be 1 by h, again 0.2 multiplied by delta on f of x naught. So, it is 2.4. Then minus del square, so 8 by 2, then plus del cubed by 3 on f of x naught. So, it is 9.60 by 3 minus del power 4, so minus 3.84 by 4. So, evaluate this, and that turns out to be 3.2. So, you are able to make use of the information given about the function at a set of discrete points in estimating the derivative of the function at any of these nodes using the operators, namely the forward difference operator and the backward difference operator. So, this is just to illustrate that one can get an estimate of the derivatives of a function for which interpolation polynomials which interpolate the function are available to us. One can get the corresponding table of differences depending upon where the information about the derivative is required, and then the estimate can be obtained. So, we almost have come to the end of our discussion on numerical differentiation. So, I will close this section on numerical differentiation with a small remark. So, it all looks nice, namely one can obtain numerical differentiation methods using method of undetermined coefficients for the derivatives of a function whose values are specified only at a certain set of discrete points. And these formulas can involve any number of points, namely you can get a 3-point formula or a 2-point formula, or if you want to specify the accuracy, then depending upon what accuracy and what class of functions f that you have been given, then you can accordingly write down the numerical differentiation formula using method of undetermined coefficients. In addition, polynomial interpolation gives us an estimate of the derivative at the nodes and also at any point x in the interval where the function f of x is known, which was discussed in the theorem that we considered in the previous class. Or one can also get an estimate of the derivatives in terms of the operators. So, it all looks nice. We will be able to get estimate of any order derivative of the function provided f satisfies the requirements so that we will be able to compute the derivatives which exist and are continuous. So, now we now give a remark by saying that this numerical differentiation formulas are quite unstable, in the sense that if the given set of values about the function have rounding errors about the function values, then our method is likely to become unstable. Namely, even for small round off errors in the function values, we may get large errors or large deviations, so that the method is an unstable method. So, we would like to illustrate this by the following example. So, we should take care to see the example essentially informs you that you should make sure that the information about the function that is given in the form of a table, right, are correct, and then you can use the you can use the numerical differentiation methods that we have discussed to get an estimate of the derivative of the function. So, it is important to ensure that the information about the function which are specified in the form of a table are correct. Otherwise, your numerical differentiation methods can become unstable. So, we illustrate this by the following example. So, let us take the following simple example. Suppose say we are given the function values at 2 points, namely minus h and plus h. I can interpolate this function by a linear polynomial p1 of x. Remember that f of minus h and f of h, they involve rounding errors. Namely, the actual value, let us denote it by f star at minus h, so that f of minus h is this plus some epsilon 1, which is the rounding error. And similarly, f of h is f star of h plus some error, which is epsilon 2. So, f star of minus h and f star of h are the actual values. The information given to us has rounding errors. That is how we start, because we would like to show that when there are rounding errors and the set of values given to us is not correct, then numerical differentiation may lead to unstable process. So, I have information at 2 points, so I can approximate this function by a linear polynomial passing through these 2 points. So, I write down the Lagrange polynomial, that is L naught of x into f at minus h plus L1 of x into f at h. What is L naught of x? It is x minus h by minus h into f at minus h. L1 of x will be x minus minus of minus h into f at h. So, this is the first degree linear polynomial that approximates this function. P1 of x is equal to f of minus h plus f of h minus f of minus h divided by 2h into x plus h. So, I compute f dashed of x, which is the derivative of f, and we know that it is approximated by the derivative of p1 of x. So, p1 dashed of x will be f of h minus f of minus h by 2h into the derivative is 1 here. So, p1 dashed of x is the term on the right hand side. So, it involves the function values which are specified, the difference between them by 2h. So, this is a constant. So, there are 2 points minus h and h. So, the function values at this point minus the function value at this point are used. So, the difference between that by 2h, you recall that this such a formula was derived yesterday using method of undetermined coefficients, namely it approximates the derivative at the center point. So, whatever that you have got is an approximation of the derivative of f at the center points, and that is f at h minus f at minus h divided by 2h. So, what is it that you have got by performing differentiation? You essentially have a numerical differentiation formula that estimates the derivative of f at the point 0, which is this. So, let us see what is it. So, f dashed of 0 is essentially estimated as, what is f of h? F star of h plus epsilon 2 minus f of minus h is f star of minus h plus epsilon 1 divided by 2h. So, this is f star of h minus f star of minus h divided by 2h, then plus epsilon 2 minus epsilon 1 divided by 2h. Recall, f star of h and f star of minus h are the actual values which must have been given to us in the table of values. But there were some round off errors, and so f dash of 0, which is estimated as this, is such that as h goes to 0, the first term f star of h minus f star of minus h by 2h in the limit as h goes to 0 will give you f dash of 0. However, if you look at the second term, epsilon 2 minus epsilon 1 is some fixed constant, and so as h tends to 0, this second term tends to epsilon 2 minus epsilon 1 by 2h tends to infinity. So, the estimate of f dash of 0 is such that as h tends to 0, the first term gives f dash of 0, but the second term goes to infinity as h tends to 0. So, for small values of h, when you take the information at a set of points and take your h to be very, very small, then the first term does give you f dash of 0, which is fine, but the second term which occurs due to round off error goes to infinity. So, you think that okay, I will make my h large. So, if you make your h large in such a way that this epsilon 2 minus epsilon 1 by 2h may become smaller and smaller, but the first term will be a poor approximation for f dashed at 0. So, you neither can have h to be very, very small, in which case the term coming out of the round off errors becomes very, very large, so that the error becomes large in estimating f dash of 0, or when you make h very, very large, the term becomes smaller, but this is not a good estimate of f dash of 0, it is a poor estimate of f dash of 0. So, this tells you that there is an optimal h that must be taken in order that this numerical differentiation formula will give you an estimate which is accurate enough to be considered for computations. So, this example essentially illustrates the fact that numerical differentiation formulas can become unstable, namely for small changes in the actual values of the form epsilon 1, epsilon 2, they are very small. Say you get large deviations in your final estimate of the derivative when the step size h becomes very small, and therefore the method can become unstable, and therefore you must ensure that the information that is given to you in the form of table of values, when you use them to get an estimate for derivatives of the function whose information is provided to you, is accurate, is correct. It does not involve any rounding, or round off errors are not incorporated in the set of values which are given to you. So, with this we close this section on numerical differentiation, and we shall move on to the section on numerical integration, where again we make use of this polynomial interpolation of approximating a function f which has to be integrated between suitable limits. So, let us see how we can obtain numerical integration methods to evaluate certain definite integrals. So, I am interested in evaluating an integral of the form, say integral a to b f of x dx. So, in case f of x is given at a set of discrete points in the interval a b, or when f of x is such that the methods which are known to you, like substitution, integration by parts, cannot be applied to this integral a to b f of x dx, then you require some methods by means of which you should be able to have an estimate of this integral. In such cases, we resort to the numerical integration methods and use them to get an estimate of this integral. Here again polynomial interpolation comes to our rescue. Suppose say we are given integral a to b f of x dx which has to be evaluated. Then we can choose points x0, x1, x2, etc. xn in this interval a to b, evaluate this integral by approximating this function f of x by an interpolating polynomial such that f of x is sigma k is equal to 0 to n L k of x into f of x k. Namely, f of x is approximated by a polynomial of degree p n whose degree is at most n, and so we have taken a Lagrange interpolation polynomial. And so, integral a to b f of x dx will be integral a to b p n of x dx, and that is integral a to b sigma k is equal to 0 to n L k of x into f of x k. So, this will be sigma k is equal to 0 to n into integral a to b L k of x dx multiplied by f at x k. K is equal to 0 to n. So, k equal to 0 to n integral a to b L k of x into f of x k. So, what are these L k of x? They are all polynomials, we have already seen. What is this L k of x? L k of x will be equal to x minus x naught, x minus x1, etc., x minus x k minus 1, x minus xk plus 1 into x minus xn divided by xk minus x naught into xk minus x1 etc. xk minus xk minus 1 xk minus xk plus 1 and so on xk minus xn. So, Lk of x are all polynomials and therefore, we know how to integrate these polynomials between a and b. So, we write down the result. So, that will be sigma k is equal to 0 to n. We call that value when Lk is integrated between a and b as ak. So, ak into f of xk. So, we have integral a to b f of x dx to be approximated by integral a to b Pn of x dx, which is equal to sigma k equal to 0 to n ak f of xk. So, find out ak and then take this sum from k equal to 0 to n of ak f of xk, that will give you an estimate of integral a to b f of x dx. In case the points x0, x1 etc. are equally spaced, then the resulting method is called Newton-Cotes formula. So, in case xi's are equally spaced, namely xi is x0 plus ih for I is equal to 0, 1, 2, 3 up to n, then integral a to b f of x dx, which is approximated by integral a to b Pn of x dx, which is equal to sigma k equal to 0 to n an into f of xk. This is called Newton-Cotes formula. Newton-Cotes formula. So, let us work out the details for a simple case. Say when n is equal to 1. When n is 1, what is given? You are given the 2 points x0 and x1 and the corresponding function values, which I denote by f0 and f1. So, I am taking these 2 points x0 and x1 where belonging to the interval a b such that x1 minus x0 is h. And I would like to derive a Newton-Cotes formula when n is equal to 1 by taking 2 points x0 and x1. I can take that x0 and x1 to be such that x0 is a and x1 is b, so that b minus a will be equal to h. I can use the endpoints and then write down this formula. So, what will be my p? So, here n is 1. So, I can approximate the function f by a linear polynomial, which will be x minus b by a minus b into f at b plus x minus a by b minus a into f at a. This is a linear polynomial that approximates f. So, f of x is approximated by this. So, I require integral a to b f of x dx. So, that is integral a to b p1 of x dx, and that will be equal to integral a to b x minus b by a minus b into f of b into dx plus integral a to b x minus a by b minus a into f of a into dx. So, in our notations, what will be the formula? The formula is sigma k is equal to 0 to n is 1 a k, right, so this is ak into f of xk. So we will get a naught into f of x naught plus a1 into f of x1, that is f1. So what is a naught? A naught is going to be nothing but integral a to b x minus b by a minus b. So x minus b by a minus b into f at a plus x minus a by b minus a into f at b. Lagrange interpolation polynomial is written. So the points are a and b. So x minus b by a minus b into f of a plus x minus a by b minus a into f of b. So here this will be a and here it is b. So we have to now evaluate a naught and a1. So a naught will be x minus b by a minus b integration with respect to x. So that is 1 by a minus b into integral a to b x dx minus b into x between a and b. So that will give you 1 by a minus b, b square by 2 minus b square minus a square by 2 minus ab. So that will give you 1 by a minus b into b square minus a square by 2 minus b square minus ab, minus b square minus ab. So this gives you 1 by a minus b into, I can write this as b minus a into b plus a by 2 minus b into b minus a. So 1 by a minus b into b minus a factor can be taken out. So I am left with b plus a minus 2b by 2. So that will give me 1 by a minus b into b minus a into, this gives me a minus b by 2. So the value of a naught is b minus a by 2. Let us now evaluate the second constant a1, which is integral a to b x minus a by b minus a. So that will be 1 by b minus a x square by 2 minus ax between a and b. So that will give you b square by 2 minus ab minus a square by 2 minus a square. So this will give you 1 by b minus a into b square minus a square by 2 minus ab minus a square. So which is 1 by b minus a. You can write this as b minus a into b plus a minus a into b minus a. So you remove the factor b minus a. So you have a b plus a minus 2a by 2, and that gives you b minus a divided by 2. So that is your a1. So you have computed both a naught and a1. So that gives you the result for approximation of the integral f of x dx, which is integral a to b p1 of x dx, which is a naught into f naught. F naught is f at x naught and x naught is a. So a naught into f of a naught is b minus a by 2. So b minus a by 2 into f at a plus a1 into f1, x1 is b. So f1 is f at b. So that gives you a1, which is b minus a by 2 into f at b. So it is b minus a by 2 into f of a plus f of b. But b minus a is the length of the interval, and we have said that that is equal to say h. So, h by 2 into f at a plus f at b. So, this is an estimate of the integral when you approximate the function by a linear polynomial p1 of x. And what do you observe? You have the endpoints a and b of the interval across, and you require the integral of a to b f of x dx, and the function values are f of a and f of b, and the length of the interval is b minus a, and the method, the Newton-Cotes method that we have derived for by taking n is equal to 1 gives you a result which says that this integral is h by 2 into sum of the end ordinates of that interval a and b. So, you simply take the ordinates at the end points a and b, then the length of the interval by 2. So, half the length of the interval into the sum of the end ordinates will immediately give you the result, namely an estimate of integral a to b f of x dx. And you surely know that there is some amount of error that is incurred in this estimate. So, you have to determine what is the error that is incurred, namely integral a to b f of x dx minus h by 2 into f at a plus f at b. What is this error which has to be determined? So, we will continue with the error analysis of Newton-Cotes formula derived when n is equal to 1, and then move on with n is equal to 2 and see how Newton-Cotes methods can be derived. And note that the method that we have derived with n is equal to 1, it is called trapezoidal rule. It is called trapezoidal rule. You have approximated this function by means of a linear polynomial, namely a straight line passing through the points a f of a and b f of b. And you have approximated what is integral a to b f of x dx. It is the area bounded by the curve y is equal to f of x and the ordinates at x is equal to a and x is equal to b, namely you require this shaded area. But what did you do? You approximated f of x by means of a straight line passing through the points, and therefore you computed only the area under this line, namely you computed the area of the trapezium bounded by the parallel sides, namely at x is equal to a and x is equal to b, multiplied by the height which is equal to h. So, h by 2, what is the area of the trapezium? It is h by 2 multiplied by sum of the parallel sides. So, h by 2 into f of a plus f of b, and that is what you got as your formula. So, you got the area as the area that is given here, and therefore, the error that has been committed by you is that you have not incorporated the area that is now marked. So, that much amount of error has been committed by you in approximating this function f of x by a linear polynomial. So, what is it is what we need to determine. So, we shall perform this error analysis in the next class.